Going to look at volumes, and we're going to create volumes by taking a region, laying it, so we're going to take a region, we're going to lay it flat, and we're going to put on top of it triangles, semicircles, squares, and make a three-dimensional shape. Are y'all with me? So our very first job then is to look at problem 3. I want to go through this with you because I read your surveys, and I also graded your quizzes. We don't remember stuff, do we? Very well. So I gave everybody full credit on the quizzes. A lot of people might have failed the quizzes, but we'll talk about those in recitation next week. Okay. Anyways, I know it was a pop, true, false quiz. It was really, but anyways, doesn't matter, Tina, shut up, be quiet. All right, here. Oh, we will talk about that next time, but I did read your surveys, and a lot of surveys said they left a little confused on Wednesday, so I want to go through a problem slowly, methodically, carefully, and then I'm going to give you one to try, okay? That's what we're going to do to start today. So, a solid has as its base the region bounded by the curves y squared equals 4x and x equals 4. Every cross-section perpendicular to the x-axis is a square. We are tasked to finding the volume of that solid. So we want to set up an integral and find the volume of the solid. The technique that we're practicing and we're learning is taking a solid that's created by slicing it up into little slices and adding those all up. In this case, we're taking squares and we're putting them on top of the region y squared equals 4x and x equals 4. On your first exam, okay, it might seem simple, but there's some key things to keep in mind because you're going to start getting volumes of solids of revolution, Washer method, Shell method. I want to give you some highlights here as to what's important. Number 1, they're giving you a base region. So the very, very, very first thing I suggest you do is draw the base region to get a picture of what you're stacking things on. So, step 1, of course, and some people ask that we break down our processes a little bit, so I am absolutely going to go through this process real slow here. Step 1 is to identify the base that we're going to stack things on. Are y'all with me? Okay? So we want to graph y squared equals 4x. What is it? What are you guys picturing? What is y squared equals 4x? Ideas? I know a lot of you guys know what it is, but you're in my quiet class, so I might have to yell and pull it out of you. Y squared equals 4x. Anybody want to just guess, volunteer information? Yusuke? It's a parabola, absolutely. This particular parabola, because it's y squared as opposed to x squared, is sitting on its side, right? And if I don't know what it looks like, I can always go to Desmos. Do you guys know Desmos? Have you used Desmos before? So you can always go to Desmos and graph this area, which I'll do in a second in case people haven't used Desmos. But I'm just going to pick a couple points here. Let's see. Y squared equals 4x. When x is 1, y squared is 4, which puts y at 2 and negative 2. It's a parabola on its side. When x is 4, that gives me 4 times 4, which is 16. Y squared is 16, which puts y up here at 4 and negative 4. So we've got this parabola. It's a parabola. All right, so we got our parabola. And I'm going to do something. I'm going to label it. It's very important that once you start getting lots of curves, okay, that you label them so you know what they're named. Y squared equals 4x. I also have this region bounded by the line x equals 4. Is that a horizontal or vertical line? Does it go up and down or does it go side to side? Which one? X equals, Matt, it's a vertical line. It's a vertical line. X equals 4 is when x along the x-axis is always 4. So the region that I'm going to stack things on is this region right here, like a half a moon or half a circle, semicircle, but not really. It's a parabola, but I've got this region here, okay? I've got a region. And on that region, what am I doing? I'm stacking cross sections. I'm slicing sections perpendicular to the x-axis that are squares. That's the next important piece. The first important piece is what region we're going to be stacking on. The second piece is how are we stacking and what are we stacking? We're stacking squares. We're stacking squares perpendicular to the x-axis. So I don't know if you can visualize this, so I'm just going to write down, this is my base. This is the base of my square. The square, right, picture taking this region, hi AK, putting it down, and on top of that region, I'm stacking squares. Are y'all with me? Let's see if I can't visualize it a little bit. Sometimes it helps if we visualize it. So let me see if I can get this picture going for us. So we've got a parabola. We've got this parabolic region. And on top of that parabolic region, I'm stacking squares. And those squares are standing so that the base is perpendicular to the x-axis, but I'm going to stack a square. And then I'm going to get another square. Right? And then I'm going to stack another square. And then I'm going to stack another square. But I'm stacking infinitely many of these squares, right? We're just stacking squares, right? Which means that the base matches the height of each of these shapes, and we keep coming down and we keep coming down. Can you picture kind of, I know this isn't very good. That was kind of a bad, this square is not very good, but can you guys kind of picture what's happening, right? Can you see that parabola, how it's kind of still being built, right? But it kind of comes up like this. So we got this parabolic shape, and we're stacked. You see, you guys see what's, it's like a, what would you call something like this? Like a what? Like a, what is that shape? Like a door wedge? You know, like the thing you stick under a door kind of thing, maybe? I don't know. You got a name for that shape?
Oh, it's like a dreidel.
What's a dreidel?
You know what a dreidel is?
Guys, okay, so, sorry, did not mean to get on a sidetrack. Okay, here we go. So we've got a picture, a dreidel, we've got a dreidel, a doorstop, whatever you want to call it. There's our picture, but what we're charged to do is set up a volume or an integral, that can get us this volume by slicing, okay? So what's important is each slice. But what's more important is we are stacking these along which axis? Along the x-axis, which means we're adding up all these slices, we're summing them. That's what integration is. It's a huge sum, hence the symbol. No, I'm not kidding. It is a sum of things, slices, integrals, rectangles, cylinders, whatever we're summing, discs, 3-dimension, 4-dimension, single dimension, always the same. We're summing, sum along the x-axis. So that means that the thickness, so each square is like paper thin. That thickness of that square is dx. dx is the thickness of that square, that piece of paper, okay? Whatever it is that we're adding up. So dx is my thickness. Okay, now, what are we doing? We're putting squares in here, and in order to get the volume, we have to go along the x-axis, and what are my bounds? Jake, what are my bounds? What am I going from? 0 to 4, absolutely. We're adding them along the x-axis from 0 to 4. This is my base, right? My base is the bottom. And what is the area of a square? The area of a square is base squared. So really, our only job is to figure out how to put the area of this square in here. We're summing all these areas up. But we don't have b's, we have to turn that b into x, right? We need to replace that b with x. So when we talk about a vertical base, one perpendicular to the x-axis, that base stretches from this curve to this curve, top curve to bottom curve. So I'm going to write that in my notes as well because, like I said, I want to be extremely detailed on this first example. B represents the distance from the top curve down to the bottom curve. And mathematically, we simply take our top curve minus our bottom curve. So mathematically, we take the top curve minus the bottom curve. That's going to be our B value. Now, how do we get it? We have to identify our top curve. Somebody give me the top curve on this side of the room over here. What's my top curve? What is the equation of the top curve? Y equals square root of 4x, right in the middle. Okay, we got square root of 4x. And what's my bottom curve? Y equals negative square root of 4x. Can we simplify that down a little bit? 2 root x, right? Square root of 4, square root of x, 2 root x. Negative 2 root x. So that tells me, again, I'm going real slow here just for this first example so we get our whole process down. But that tells me, yes, sir. You may absolutely interrupt me. Go ahead.
I thought the graph of the radical is just the positive quadrant.
It is. It is. The graph of the radical, thank you for asking that question, Grant. The radical curve right here is the top curve only. 2 square root of x would be only that top curve. You are 100% correct. But when I throw a negative in front of it, it gives me only the bottom curve. So the negative puts me only at the bottom. And so if I want to get the distance between that upper 2 square root of x and the bottom negative 2 square root of x, I have to subtract the top curve minus the bottom curve. Gavin.
So I'm just confused on why you're using, like, instead of using, because I know, like, you can go from the sideways, you can look at perpendicular to the y-axis. So, oh, it says perpendicular to the x-axis. Never mind.
You answered your own question.
I know.
Some of the shapes on your homework go to y, and that's going to be our second thing, is to the y. Right now we're focusing perpendicular to the x. Thank you for pointing that out because, like I said, this is so important when you're reading and doing your test or any homework that you know what axis you're cutting perpendicular to. So everybody's seeing that top curve is 2 square root of x, bottom curve is negative 2 root x. When you put those together, I'm running out of space here and I feel really bad, but you have 2 square root of x minus negative 2 square roots of x gives me 2 square root of x plus 2 square roots of x, which is just how many square roots of x? 4 of them. B is just 4 square root of x. B is just 4 square root of x. Why does it have an x in it? Because we know these squares get smaller and smaller the closer you come here, and bigger the closer you come here. Those squares are changing. And when you change that distance, that's where the x comes from. Depending where that x is, that changes that distance. So what does that mean? My volume is 0 to 4. My base is 4 square root of x. To get the area of that square, it's going to be 4 square root of x dx. And so what would my volume be? It would be 16x dx. And when I integrate that, add 1 to the power, right? Divide by 2. Are you guys getting 8x squared from 0 to 4? Which is 8 times 16 minus 0, or 128. cubic units. Volume is always measured in cubic units because it's a three-dimensional volume that we're talking about, a three-dimensional space. From my problem, the area gives me square units, right? The area of a square is square units. And this dx right here, this thickness, is what gives me my cubic units. That thickness right there, that microscopic thickness gives me my third unit. And we're just integrating and adding those all up, okay? So we got cubic units going there. Here we go. Your practice right now. A solid has as its base the region bounded by the curves. Can you see it? Is it big enough? Y equals 6 divided by x. X equals 6 and y equals 5. So a solid has as its base the region bounded by the curves, y equals 6 over x, x equals 6, y equals 5. If every cross-section perpendicular to the y-axis is an equilateral triangle, what is the volume of the solid? I think what I'm going to do is take a screenshot and put. So there's our problem right there. A solid has as the base of its region the region bounded by the curves, y equals 6x, x equals 6, and y equals 5. If every cross-section perpendicular to the y-axis is an equilateral triangle, what is the volume of the solid? Set up the integral that can be used to give you the volume. So this is your challenge right here to do. So you're setting up y equals 6 over x. And if you don't know what it is, you're pulling out Desmos graphing calculator and you're graphing it. Y equals 6 over x. X equals 6. Y equals 5. What region are we talking? That is 6 over x. I like it. No, it's not. You're good. Now, you didn't draw me the other two. Where's the other two? Y equals 5.
I know.
X equals 6. You got it. No, this is good. You did good. This is your axis, right? This is your axis. This is y equals 6 over x. This is y equals 5. This is x equals 6. Oh, it is. Okay. But that doesn't matter because that one doesn't even touch what you need. Right? You only need the part that's bounded by the three curves. Right? You only need the part that's bounded by the three curves. If you can't see it, right, y equals 6 over x. And because I'm written in terms of y, that means my equations have to be x equals something. So notice, your right curve for B is x equals 6 minus, and what's my left curve? My left curve is given by the equation y equals 6 over x. But if I transform it, close, very good get, very close. Maybe you said it, but I just didn't hear it right. X equals 6 over y if you solve for x. Because we cross multiply. Let's see. Let's make sure. First multiply both sides by x, and that gives me xy equals 6. And then divide by y, right? So x equals 6 over y. So that means my left curve is 6 over y. The right curve is x over 6. Does everybody see that? The left curve is x equals 6 over y. Everybody see that? Make sure if there's any questions. Remember, this is our chance to ask. It was y equals 6x. we transformed it to be x equals 6 over y. So that's my left curve. My right curve is 6. Left curve is 6 over y. That base stretches from 6 to 6 over y. And so that means that my integral for the volume is the integral from 1 to 5 square root 3 over 4 times my base squared, which is 6 minus 6 over y dy. I have a question for y'all. How do I integrate this sucker? What would you do? Let's just talk strategy here. What would you do? Absolutely. I would too. I would first pull out the square. We don't have to do it right now, right? We don't have to integrate this right now. But Hannah says, let's pull out square root 3 over 4. What do you want to do with the rest of it? Foil it? Foil it out? If I foil it out, I get 36 minus 36 over y minus 36 over y plus 36 over y squared, right? If I multiply this out, I get this. If I'm doing it, right? And now, it looks yucky, but really, now it's really easy. Because I have a piece, minus a piece, minus a piece, plus a piece in an integral. And what can we do with things added up in integrals? We can separate those, right? True. You can separate pluses, not multiplications. I can't do this one and this one, but I can, once it's expanded, take each integral. All right, what's the antiderivative of 36? 36y, thank you. What is the antiderivative of 36 over y? AK loves math. Yes, he does. He is a math major in hiding. He just doesn't know he loves math. How do I do that last one? Not AK. Who else? Somebody else. How would I do that last one? How would I do that last one? Oh, it's 36y squared, right? Which is just 36y to the negative 2, right? And then you add 1, right? Divide by 1. So what's that? Negative 36y to the negative 1? Do you see what I mean? So integrating, even though it looks scary, is not that bad. I'm not going to finish it. I just wanted to start it for you because the problem says you don't have to go all the way down. But right now, I just wanted to show you that it's really not that bad if you break it down into smaller chunks. Okay? It's really not that bad. And then we plug 5 in and we plug 1 in and then we get numbers and we'd be all good to go. But my question is, does anybody have a setup question about how to set up this integral for this volume of this solid? Reese?
So I'm going to set up for root 3 over 4.
Yes.
Pull that out.
Yes.
Let me go to integrate with 5 and 1.
Yes.
Is it 3 over 4 is all the way on the outside of
everything?
Right.
Everything. Unless you put it in to everything. But I like to keep it out and then do all that and then at the end put it in.
Okay.
Okay.
Well, I have a question about right curve.
Okay.
What's the right? So the right curve is 6?
Yes. Good question about this here. So because we're stacking these, do you see them? We're stacking them horizontally because we're stacking these triangles up and down, right? So when it's a sideways stack, you want to go right curve minus left curve. And notice my right curve is defined by this equation, x equals 6. It's the vertical line. That's my right curve. And my left curve is defined by this bound over here, which I labeled. See, I'm good. I label things. So this is y equals 6 over x, but that's written in terms of x. Can't do that because I know I'm integrating with respect to y. So I multiply both sides by x, I divide by y, and I rewrite it. That's my left curve. So base is right 6 minus left 6 over y. Did you see that? Question, Lily?
Can you write it in terms of x if you change the bounds of the definite integral?
Well, you could, but here's the thing. You would be getting a slightly different shape. Because it's not perfectly square 5, kind of thing. It's, even though 6 over x is a perfect shape, right now, my bases are longer because they go all the way 6 units out, versus if I turn it the other way, I'm getting thinner bases. Now, a question is, the shape that you get, does it have the same volume? You see what I'm saying here? So the shape, would it be the same volume if I flipped it? Sometimes it is and sometimes it isn't. It's really kind of fascinating to think that through, to figure out whether sometimes the shapes are and sometimes they aren't, and what causes that. But yes, I'd have to be integrating perpendicular to the x-axis for that to happen. Okay? Other questions? All righty. Are you guys ready?